All right, so let's look at a seesaw as an example, teeter-totter, whichever way you say it. This one is pretty nice. It's got a barrel here, right? And these girls are playing on a ladder over a barrel. So it's interesting to see some of the ways that some of the things we know as these industrialized equipment was, or not equipment, but playground equipment. Um, how kids actually looked at them 150 years ago, and here we've got people actually making girls actually making their own seesaw. And I've got another one that I've seen that was really nice, which was a um, diving board, which was basically made out of boards nailed together and held up by rocks over a pond. That was awesome. Let's look at this though. We want to look at a teeter totter. We're going to simplify it. It's just going to be you, right? And so we're going to have, a teeter totter here. You're going to put your cousin over here, or yeah. So your cousin's over there. It's 8 years old, weighs 60 pounds, and this is some distance. I'm going to call it 6 feet. Got 6 feet there. And then you're going to want to sit over here. You're a little bit older, so you're 120 pounds. Okay, and now you're going to want to play over here at a distance where if you sit like this, you'll both balance out. That makes for the optimal teeter-totter experience. All right, so we want to find this distance here for you. What did I call that? D. Okay, so that's what we're going to do. So to look at that, we just looked at in the lecture part, the law of the lever. All right, that's FD equals little f little d. Awesome. Okay, so this is what we want to use with this data, right? 60 pounds, 120 pounds, 6 feet. I put it all in a nice little drawing so I know what each thing is. I'm going to just start putting these numbers into my equation, right? So you are bigger, so you're going to be the uppercase letters, and your cousin is smaller, so lowercase letters, like that. Okay, so we can just put these numbers in. So 120 pounds times big D is equal to 60 pounds over here times 6 feet. So let's go ahead and get these fixed up. So the first thing I do is I divide by 120 pounds. Okay, this cancels this, so we have D is equal to 60 over 120 is 1/2 times 6 feet. Okay, and then we divide that out, so we have 3 feet. So you are going to want to be 3 feet halfway through here because you weigh twice as much. Seems pretty reasonable. It's really a ratio thing. A lot of times, if you understand the ratio, how to get the ratios, you'll be able to solve a problem really quickly. Right, and so all we did was we identified that this was something we'd want to use the law of the lever for, because we had an object with a fulcrum. So we have an object with a fulcrum, right? We have things on either side. In this case, the things were you and your cousin, right? And we were asking ourselves something about the distance or the weight or something like that, given enough stuff. So in something like that, that's a good time to use the law of the lever. Then all we did was we took this data, which we sort of collected first in our drawing, and assigned it to different places. It would be nice if I assigned it correctly. And then did some math. So that's more or less all we needed to do here, was identify that this is a good problem for the law of the lever and make appropriate substitutions. All right, very good. Next up is the law of inertia. Talk a little bit about what happens when forces balance and something's moving already. And then one more example. After that, it's time for the next lecture. All right, bye now.